Tonight, we're going to explore something that seems simple, but is actually one of the most fascinating ideas in history: the night sky. You've probably looked up at stars many times before. Scholars and historians talk about them constantly when explaining ancient cultures. But here's what most people don't realize. When you truly imagine what the sky looked like to civilizations long ago, when you start to see the stars, planets, and constellations through their eyes, it changes how you understand human history. This is not just dots of light in the darkness. It's a canvas so vast and full of meaning that it shaped religion, navigation, and even early science. And by the end of this journey, you're going to understand exactly why the night sky mattered so deeply and why it guided so many lives in ways we often forget. Before we go any further, if you enjoy calm, deep explorations like this, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. The night sky stretches above in every place and time where humans have stood under it. In its vast darkness, stars are scattered like grains of sand across a black sea, each point of light distant, shining, and constant. To early humans, this ceiling of light must have seemed both immense and intimate. They could see the brightness of the Milky Way as a pale river stretching from one horizon to the other, and the gentle movement of stars as the earth rotated beneath them. Clouds drifted across, altering the scene, hiding and revealing parts of the sky. The wind shifted, and the air smelled of earth, fire, or water, changing the perception of the night, even as the stars remained steady. The senses were fully engaged, vision first and most obviously, but also hearing, feeling, and even taste and smell, as the night carried its quiet signals of the world below. In this immense darkness, patterns began to emerge. Small groups of stars formed shapes that could be remembered, used, and shared. Some were simple lines, others curved into arcs or enclosed into rough circles. Humans recognized repetition. A star would rise in the east, pass overhead, and set in the west, night after night, month after month. Others appeared at different times, returning only in certain seasons. The constancy and rhythm of the sky offered a way to mark the passage of time. Without instruments, without numbers written on paper, early observers could measure duration by the position of stars, the waxing and waning of the moon, and the shifting path of the sun along the horizon. This became the first form of recording and measuring time, a tool of survival as much as wonder. The Milky Way, faintly glowing and softly luminous, held particular significance. Its vast expanse suggested movement, direction, and flow. People could track its course and use it to find north, though the idea of magnetic north was unknown. In the absence of maps, the sky itself became a map, with landmarks and reference points that were memorized and passed down. Night after night, children learned the positions of stars from elders, tracing lines and angles in the dark and learning the stories that accompanied them. Each group of stars had a name or a story, a function or a warning. Observation was the first lesson in science, learned by watching, remembering, and predicting. Even planets were noticed, though their nature was not understood in the way modern astronomy explains them. Venus shone brightly at dawn or dusk, sometimes dominating the horizon, its steady brilliance different from the twinkle of distant stars. Mars glowed with a red tint, moving in a strange pattern against the fixed backdrop. Jupiter and Saturn were visible as slow wanderers, tracing long paths over many months. These wandering lights were distinguished from the fixed stars by careful observation. The movement of planets added a dynamic quality to the night sky, a sense that it was alive and changing, not merely a static dome. The sky itself was affected by the Earth's rotation and orbit. Seasons shifted which stars were visible. In winter, the sky seemed deep and cold, the brightest stars sharp against clear air. In summer, the air shimmered with heat, and the faint stars of the Milky Way were more subdued, yet still present. The moon waxed and waned with a predictable rhythm, marking time not only for practical purposes, but also for storytelling. Its cycles governed the timing of certain human activities: when to plant, when to harvest, when to gather. The phases of the moon were perhaps the first regular measurement of change, a natural clock against which humans could compare their lives. Silence was part of the experience. Without artificial lights, cities, or engines, the night was filled only with natural sounds: the rustle of leaves, the movement of animals, the distant flow of rivers, and occasionally the howl of predators. These sounds set a stage for the sky, giving it scale and contrast. A meteor streaking across the darkness would be shocking in its suddenness, its fleeting fire igniting stories and warnings. The clarity of the stars depended on air quality, the absence of dust or smoke, the crispness of cold nights, or the moisture in the air that blurred the distant lights. Observation was not passive. It was an active engagement with the environment, the sky, and the senses all at once. Early humans were constrained by geography. Latitude and elevation affected what they could see. Near the equator, the stars moved in long arcs, passing nearly overhead, and the Milky Way split into two visible sections. Farther north or south, the angles changed. Stars circled around poles, and some constellations never rose or set. This created a diversity in night sky experience. Groups living hundreds of miles apart observed different patterns, different seasonal stars, and different markers for agricultural or hunting cycles. Yet similarities emerged. Many societies noticed the same bright stars, the same moon cycles, and the same paths of the planets. This shared perception created a common language of the night sky that could be adapted into local culture. Stories emerged from observation. The shapes in the stars were connected to myths, to animals, to ancestors, or to natural forces. These stories were mnemonic devices, helping people remember the locations and significance of the stars. They also gave moral or social lessons, embedding cultural knowledge within astronomical observation. The same star could represent a hunter in one culture, a hero in another, or a warning in yet another. These stories evolved with repeated observation, refined over generations, and became a bridge between empirical knowledge and cultural identity. The first forms of record keeping were also connected to the sky. Simple marks on stones, bones, or clay could track the movement of the moon, the rising of certain stars, or the timing of eclipses. These were not abstract mathematics, but practical tools. Observations frozen in time to assist with planning, prediction, and ritual. Over centuries, these records accumulated into more structured calendars, helping communities prepare for seasons, migrations, and agricultural cycles. The night sky was not just beauty or inspiration. It was a living guide, essential to survival and organization. Finally, the night sky offered a sense of scale and permanence. While life on Earth was fleeting, the stars remained. Generations could observe the same patterns, noting changes that occurred over decades or centuries. Meteor showers, comets, and supernovae provided rare but dramatic exceptions to the constancy, drawing attention and inspiring awe. Even without understanding the physics behind them, ancient humans recognized that the sky was both reliable and capable of surprise. This duality, permanence and change, pattern and anomaly, defined the first human relationship with the cosmos. Its sky became the foundation for all later study, observation, and interpretation. The quiet, enduring canvas on which humanity first measured time, meaning, and place. As humans became more familiar with the stars, they began to notice not only their beauty, but their utility. The movement of the sky was closely watched, because it marked the passage of time in a way that could be relied upon. The rising and setting of certain stars or constellations occurred at the same points in the year, allowing people to predict seasonal changes with surprising accuracy. The first observations were probably linked directly to survival. Hunters noted which constellations appeared when particular animals migrated or bred. Farmers observed which stars rose before rains or frosts. The sky became a natural calendar, a guide to movement, planting, harvesting, and even the timing of social gatherings. Constellations emerged as tools of orientation, as well as storytelling. Certain bright stars became markers in the landscape of the sky. The North Star, visible in the northern hemisphere, provided a fixed point around which the rest of the sky appeared to rotate. Its position remained constant while other stars circled it, giving humans a reliable indicator of direction at night. This was crucial for travel, foraging, and migration. In places without permanent landmarks, the stars served as guideposts. Observers learned to navigate by following the rising and setting of familiar constellations, recognizing their paths across the seasons, and adjusting for shifts in the horizon caused by the tilt of the Earth. The connection between celestial observation and seasonal cycles is evident in early calendars. Stone structures like the circles at Gösek in Germany or the alignments at Nabta Playa in Egypt show careful planning based on the position of the sun and certain stars. These sites mark solstices and equinoxes, demonstrating that ancient people had developed methods to predict the timing of key events in the year. Observing the sky allowed them to anticipate changes in weather and light, and to prepare for periods of abundance or scarcity. In this way, astronomy and survival were intertwined. The careful study of the heavens was a practical skill, vital for sustaining life. The movements of the moon were particularly important. Its phases were easy to observe and provided a simple, repeating rhythm that could structure months. Some cultures combined lunar and solar observations to create calendars that were surprisingly accurate, adjusting for the fact that 12 lunar cycles do not perfectly match a solar year. These adjustments, often marked by intercalary days or months, show that ancient observers were aware of the limits of simple counting and the need for careful observation over long periods. The sky demanded attention over years, not just nights, for its guidance to be reliable. Comets, meteors, and eclipses, though less predictable, were also recorded and interpreted. Their appearances could signal danger or change, and early observers noted patterns when they could. Observations were combined with practical planning. If a bright star appeared at a certain time before harvest, it might be interpreted as a signal to begin gathering crops. The sky and the earth were not separate. Their movements were read together to make decisions about survival. Observation became a discipline, a way of connecting daily life with the greater patterns of the natural world. Seasonal variation in the sky was noticeable even without instruments. In winter, certain constellations would rise earlier in the evening, dominating the night. In summer, other patterns took their place. Observers could track the progress of the year by watching which stars were visible at sunset or sunrise. The first hints of formal calendars may have come from noticing these patterns and linking them with recurring natural events. Flooding of rivers, migration of animals, or flowering of plants. These connections between sky and earth formed the earliest predictive models, simple yet effective tools for planning and survival. Evidence from archaeological sites supports these interpretations. Many early settlements, temples, and ceremonial sites are aligned with solstices, equinoxes, or particular star risings. These alignments are not accidental. At sites like Stonehenge in England, the arrangement of massive stones allows for precise observation of the sunrise on the longest and shortest days of the year. The builders had no telescopes, no modern tools, yet their careful positioning reflects centuries of accumulated knowledge about the sun's path and the shifting backdrop of stars. Observing the sky was not a pastime. It was an applied science, learned through careful attention and repeated measurement. The practical use of constellations also extended to navigation beyond land. Coastal peoples and travelers on rivers noted the stars, reflections in water, and the timing of their rising and setting relative to their journey. Certain star patterns were visible only at specific latitudes and times, providing clues to location and direction. Without compasses, the sky was both map and clock. Observers became adept at reading subtle changes, noting the angle of a star above the horizon or the distance between two stars as markers for latitude or timing. These skills required patience, memory, and careful tracking, passed from one generation to the next. Human observation was keenly attuned to brightness and color. Stars like Sirius, Aldebaran, and Rigel were singled out for their prominence. The difference between red, blue, and white stars was noted even without understanding stellar temperatures. Patterns were recognized not just for position, but for luminosity. Brightness helped identify stars that were reliable indicators of seasonal changes. Over time, people could anticipate events by correlating brightness with rising points and movement. This systematic attention to detail formed the foundation for more formal astronomy, linking observation with prediction. The night sky also functioned as a social calendar. Certain celestial events marked festivals, gatherings, or rituals. Communities used the sky to synchronize collective activities, ensuring that planting, hunting, or trading occurred in a coordinated fashion. By observing the predictable paths of stars and the irregular appearances of comets or eclipses, societies could align human activity with natural cycles. In this sense, astronomy was deeply practical. It connected the cosmos with social, economic, and agricultural needs. Knowledge of the sky became both a scientific pursuit and a tool of community survival. Observation extended to careful counting. Early humans noticed the intervals between the rising of stars or the repetition of lunar phases. Some cultures recorded these intervals on bones or stones, making notches or marks to track time quantitatively. Though simple, these records allowed for predictions beyond immediate experience. With enough repetition, observers could forecast celestial events years in advance. This quantitative awareness, combined with pattern recognition, turned the night sky into a reliable instrument for planning and action. In addition to survival and scheduling, the sky offered an early sense of scale and distance. Observers recognized that some stars were always present, while others appeared only seasonally. They saw that planets moved differently than stars and began to categorize the types of celestial objects they encountered. The constant movement of the heavens taught humans about regularity and change. Night after night, they recorded what appeared, when it appeared, and how it moved. Observation became an exacting practice. balancing attention to detail with awareness of the large patterns that govern the cosmos. The integration of sky observation into daily life required memory, storytelling, and teaching. Knowledge of star positions, lunar cycles, and seasonal patterns was shared orally, passed down in families and communities. Myths, songs, and poems preserved precise information about celestial events, often encoded in memorable ways. This allowed people to carry knowledge forward, even without written language. Observation, prediction, and storytelling were interconnected, forming the first educational system focused on understanding the natural world through the lens of the night sky. Practical observation also included weather forecasting. Clouds, humidity, and temperature could affect the visibility of stars, but changes in these conditions often correlated with approaching storms or seasonal shifts. People learned to interpret these signals alongside celestial patterns. A particular star's visibility at dusk could suggest the timing of rainfall. Observers connected sky and earth in an empirical way, noticing correlations without modern instruments or scientific theory. Knowledge gained through careful attention allowed humans to adapt to changing conditions with remarkable precision. Over time, observation became systematic. Groups began to designate specific times and places for watching the sky. Particular hills, riverbanks, or clearings were chosen to allow unobstructed views. Night after night, observers would note the appearance and disappearance of stars, the position of the moon, and the angle of the sun at dawn or dusk. These repeated observations enabled predictions of the solstices and equinoxes, marking key points in the year. Humans were creating the first scientific record, using careful observation, memory, and physical markers in the landscape to extend their understanding of time and season. Tracking migrations and animal behavior remained closely tied to celestial knowledge. Hunters noted that certain prey appeared only when particular stars were visible. They correlated the first flowering of plants, the arrival of insects, or the movement of herds with the positions of constellations. The night sky acted as a universal reference frame, linking multiple aspects of the natural world. Humans were not passive observers. They were actively seeking patterns, using the sky as a tool to organize their environment and increase their chances of survival. The sky's practical uses also informed early architecture. Shelters, granaries, and ceremonial structures were often aligned with celestial events. Orientation towards the rising sun on the solstice, the appearance of Venus at dawn, or the full moon at a particular horizon point, shows that observation was not limited to open fields. Human constructions became extensions of the sky, capturing knowledge in stone and wood. These alignments illustrate a sophisticated understanding of cycles and angles, demonstrating that the earliest humans were careful and precise in their study of the heavens. In all of these ways, observation of the night sky became inseparable from daily life. It was a tool for survival, a guide to movement and planting, a marker of time, a framework for storytelling, and a source of communal cohesion. Early humans connected the positions of stars, the phases of the moon, and the seasonal motion of planets with immediate and long-term needs. Observation required patience, attention, and transmission of knowledge, and through it, the night sky became an essential instrument for life on Earth. The careful tracking of celestial patterns was the first form of applied science, and it laid the groundwork for every subsequent step in human understanding of the cosmos. The Milky Way stretched across the night in a way that early humans could not ignore. In places untouched by fire or settlement, the sky was deep, dark, and clear, allowing the full brilliance of the galaxy to appear. It looked like a soft, glowing river, pale against the black of space, filled with countless points of light. Its glow was subtle yet persistent, a faint smear of white that traced a wide path from horizon to horizon. Within this band, denser areas glimmered more brightly, revealing clusters of stars that seemed to pulse in the darkness. Without telescopes or lenses, humans could still discern variation, noticing patches of concentration and gaps where fewer stars appeared. The Milky Way was a natural feature of the night, a constant presence that guided orientation and inspired wonder. Stars within the Milky Way were not evenly distributed. Some appeared in bright clusters that stood out clearly against the surrounding darkness. These clusters were often associated with important points in the calendar, appearing at predictable times in the year and marking seasonal change. The Pleiades, visible in many parts of the world, rose at the same point in the year to indicate planting or hunting seasons. Orion, with his belt and shoulders, became a clear landmark in winter skies, while other bright stars such as Sirius dominated the southern horizon in certain seasons. The contrast between bright and faint stars allowed humans to recognize both individual stars and collective patterns, giving a dual sense of scale and structure to the night sky. Planets moved differently than stars, a subtle distinction early observers learned to notice. Venus shone with unusual brightness, dominating twilight hours, while Jupiter and Saturn wandered slowly among the fixed stars. The motion of these wandering lights added a dynamic element to the night. Observers noticed that planets did not twinkle as much as stars, and sometimes changed position relative to the fixed constellations over weeks or months. This understanding formed the basis for recognizing different types of celestial objects. The distinction between stationary stars and wandering planets was simple to perceive but deeply significant, marking a first step towards systematic observation of the cosmos. Occasionally, comets appeared, startling in their brightness and motion. Unlike stars or planets, they moved noticeably across nights, leaving tails that pointed away from the sun. Meteors flashed briefly, cutting arcs through the darkness. These events were rare and unpredictable, yet they were recorded in memory and in early markings. Observers began to associate them with unusual occurrences, such as shifts in climate, natural disasters, or societal events. Even without understanding the physics behind them, humans recognized that the heavens could change suddenly and dramatically. This awareness fostered both caution and curiosity, blending empirical observation with storytelling. Storytelling and myth became deeply connected to what could be seen in the Milky Way. Its band of light inspired narratives about rivers, paths, and boundaries in the sky. Bright stars often represented important figures, animals, or deities. In many cultures, clusters like the Pleiades were linked to agricultural cycles or seasonal myths. Nebulae, faint and cloudy to the naked eye, were sometimes imagined as spirits, creatures, or sacred objects. The sky functioned as a canvas for cultural expression, but also as a practical map, a guide for understanding time, direction, and the rhythms of the natural world. Oral traditions encoded both observation and meaning, preserving knowledge of celestial patterns through generations. Visibility of the Milky Way and stars depended heavily on location and conditions. At higher latitudes, certain stars never rose above the horizon, while at the equator, nearly the entire celestial sphere could be observed over the year. Air quality, humidity, and seasonal weather affected clarity. Cold, dry nights provided the sharpest views, while warm, humid, or dusty conditions blurred faint stars. Human observers were attuned to these variations, learning when the sky offered the clearest insight and when observation might be obscured. They adapted their practices accordingly, establishing observation sites in elevated or open areas to maximize visibility. The structure of the Milky Way itself suggested direction. Its faint river of light spanned the sky diagonally in many regions, providing a frame of reference. Travelers could use its orientation to determine cardinal directions when landmarks were absent. Over time, recognition of this structure allowed for increasingly precise navigation, both on land and across waterways. Its diffuse glow also provided a reference for relative brightness, helping observers differentiate between stars of varying intensity and plan the timing of activities such as night travel or ritual events. Clusters within the Milky Way acted as natural signposts. Groups of stars were easily remembered, their positions forming landmarks against which other celestial events could be compared. By tracking these clusters, humans could anticipate the rising and setting of nearby stars, planets, or the moon. Observation over many years revealed subtle shifts caused by the slow movement of stars across centuries, though these changes were imperceptible within a single human lifetime. Even so, early observers noticed recurring patterns with remarkable accuracy, laying the foundation for predictive astronomy and the recording of celestial cycles. The sky's patterns were also linked to animal behavior and seasonal events. Hunters and gatherers noticed that particular constellations appeared at the same time as migrations or breeding seasons. The Milky Way, stretching overhead, could indicate general direction and latitude, while specific bright stars signaled precise timing. The repetition of these patterns allowed humans to synchronize activities with nature, forming a practical knowledge system rooted in careful observation of light and motion. This integration of sky and land became central to survival, influencing hunting, planting, and ceremonial timing. Human perception of the Milky Way was not limited to pattern recognition. It included emotional and psychological response. The river of stars suggested movement and scale, connecting individual experience with the vastness of the cosmos. Even without scientific explanation, early humans grasped that the sky had structure, depth, and rhythm. Its appearance changed nightly, seasonally, and geographically, yet its overarching presence was stable and reliable. This constancy allowed humans to form expectations, to predict events, and to create shared frameworks of understanding that could be passed from one generation to the next. Observers also noticed differences in color among stars. Some had a subtle red or orange hue, others a cool blue-white tone. These variations became markers for identifying stars or groups, allowing easier communication and teaching within communities. Bright red stars, for example, often drew attention, serving as fixed points against which the motion of planets or the moon could be measured. The Milky Way's diffuse background provided context for these points, allowing observers to orient themselves and track changes over weeks and months. This combination of brightness, position, and color made the night sky an intricate system of markers for navigation, timekeeping, and cultural storytelling. Comets and meteors, though occasional, reinforce the importance of attentive observation. Their sudden appearances emphasize the contrast between predictable celestial cycles and rare, unpredictable events. They were recorded in memory and in early inscriptions, sometimes linked with historical events or natural phenomena. These fleeting lights required repeated observation of the regular stars to recognize their unusual movement. Such events strengthened the discipline of watching the sky, encouraging careful record keeping and the development of symbolic representations in myths and early written forms. Observation of the Milky Way also encouraged the creation of early visual aids. Humans traced lines in the sand, scratched marks on stones, or arranged sticks to mark significant stars and clusters. These efforts suggest an awareness of structure and scale, with the Milky Way as a backdrop for measuring angles, distances, and positions. Tools were simple but effective, serving as extensions of the eye and memory. By combining direct observation with physical markers, humans could track movement over months and years, gradually building a body of knowledge about the night sky that transcended individual experience. Seasonal shifts in visibility provided natural markers for planning and ritual. The appearance of Orion in winter, the Pleiades in late autumn, or Scorpius in summer, offered predictable cues for timing activities. The Milky Way's orientation changed gradually with the seasons, providing a subtle clock that could be read by attentive observers. By learning to recognize these cues, humans could coordinate agricultural and hunting activities, schedule communal gatherings, and prepare for environmental changes. Observation of the Milky Way was thus both a scientific and practical endeavor, connecting perception, prediction, and action. The naked eye view also allowed early humans to develop a sense of relative position. By comparing the distance between stars, noting the angles formed, and recognizing recurring patterns, they created a mental map of the sky. Bright clusters became anchors, and the faint background of the Milky Way provided context. Over time, this mental mapping grew more precise, guiding navigation, ritual alignment, and teaching. Knowledge of the night sky became an integral part of human culture, shaping both practical decisions and imaginative thought. Human culture incorporated these observations into social and spiritual frameworks. The Milky Way was often seen as a path or river for spirits, ancestors, or deities. Its clusters and brightness guided myth and ritual. Yet these interpretations did not replace practical observation. They were intertwined. Understanding the night sky required attentiveness to both its physical reality and its cultural meaning. Early humans integrated empirical knowledge with symbolic meaning, creating a rich, multi-dimensional engagement with the heavens that supported survival, communication, and identity. Finally, observation of the Milky Way reinforced the importance of time. The slow movement of the stars and planets across the sky formed a natural clock, observable nightly. Repeated observation allowed humans to anticipate events months in advance. Festivals, planting seasons, hunting cycles, and migrations could all be coordinated using knowledge of the stars. The Milky Way's presence was constant, yet subtly changing with the seasons, providing a rhythm for life that was both predictable and awe-inspiring. Through this band of stars, early humans connected with the cosmos, learning to see patterns, measure time, and navigate both land and imagination. Across the world, humans noticed the same night sky, but interpreted it in different ways. In Mesopotamia, the Sumerians and later Babylonians traced patterns among bright stars, dividing the sky into constellations that guided agriculture, ritual, and civic life. The stars of the zodiac, including Aries, Taurus, and Leo, were identified not just for navigation, but also for recording the passage of the sun through the year. Each constellation had a name, a story, and a function. They were linked to gods, seasons, and events on Earth. The constellations provided a structured framework in which celestial events could be observed, remembered, and communicated across generations. In Egypt, the sky was equally important but used differently. the stars were closely tied to the Nile and its floods. The heliacal rising of Sirius, the brightest star in the night sky, heralded the annual inundation. Temples and pyramids were aligned carefully to follow star paths, ensuring that sacred structures mirrored the movement of the heavens. Egyptian constellations often reflected animals or gods, blending practical observation with spiritual meaning. Orion was connected to Osiris, representing cycles of death and renewal, and other groups of stars formed recognizable figures that were important in burial practices, navigation, and timing of festivals. Far to the east, Chinese observers recorded the positions of stars and planets in meticulous detail. They divided the sky into regions, using a system of mansions that marked the moon's path and tracked planetary motion. The Chinese constellations often represented mythological creatures, historical figures, or bureaucratic structures. Bright stars were associated with emperors, states, and auspicious events. Observations were maintained in written records, providing continuous tracking over centuries. The Chinese system demonstrates a formalized approach to understanding the sky, linking pattern recognition with administrative, agricultural, and ritual needs. In Mesoamerica, cultures such as the Maya and the Aztec also relied heavily on star observation. They noticed the rising and setting of particular stars and planets and used these observations to structure calendars, ceremonies, and agriculture. Certain constellations were identified with gods, animals, or mythological events, connecting celestial cycles with earthly life. Alignments in temples and pyramids often corresponded to solstices, equinoxes, or the appearance of Venus. The Maya, for instance, recorded complex movements of Venus, linking them to wars, ceremonies, and planting schedules. Observing the sky was both practical and symbolic, integrating cosmic patterns into daily existence. Despite differences in culture, similarities emerge across civilizations. Bright stars and easily recognizable clusters were consistently chosen as markers. Orion, the Pleiades, and Sirius appear prominently in multiple systems. Humans across continents were drawn to the same features of the sky, patterns of light that were bright, fixed, and predictable. Cognitive processes were similar. Observers noticed regularities, traced shapes, and connected stars into meaningful forms. The act of pattern recognition, taking a random arrangement of points and imposing structure, is universal, demonstrating the shared mental framework humans use to make sense of the cosmos. Constellations were shaped by local environment as well as cultural imagination. In northern latitudes, constellations often emphasized linear arrangements or figures that fit circumpolar patterns, while near the equator, more circular and broad groupings were common due to the full range of sky visible throughout the year. Observers adapted their mental maps to the portion of the sky that was most relevant to their survival and society. Agricultural needs, hunting patterns, or spiritual practices influenced which stars were highlighted and how clusters were interpreted. Culture, necessity, and observation were interwoven, shaping the night sky in different ways across regions. The process of recognizing constellations required attention, memory, and communication. Small communities taught the positions of stars to the young, using songs, stories, and gestures to encode information. Mnemonics helped remember which stars rose at which time of year, which were bright enough to be seen in early evening or pre-dawn hours, and which clusters marked important directions or seasons. Cognitive recognition was aided by repeated observation over months and years. The ability to extract meaningful patterns from randomness was central to the creation of constellations, linking perception with social and practical knowledge. constellations also served as tools for orientation. The North Star and other circumpolar stars in the Northern Hemisphere provided constant reference points. The apparent rotation of the sky around these points allowed travelers to maintain direction even without landmarks. In the Southern Hemisphere, different stars served similar roles. Knowledge of these markers was practical for movement, trade, and seasonal migration. This practical function existed alongside myth and story, demonstrating a dual approach to the night sky: observation for survival and interpretation for culture. Over time, some patterns became widely recognized across cultures through trade, contact, or independent observation. Similarity in human perception meant that even distant peoples often identified the same bright stars and clusters, yet interpretation varied widely. Orion might be a hunter in one region, a god in another, or a celestial representation of a ruler elsewhere. Pleiades could mark the start of planting, the tears of a mythic figure, or the return of birds for migration. Despite differing narratives, the empirical observation remained consistent. These stars appeared in predictable locations at predictable times. Mythology and societal values were embedded in constellations. Bright stars often represented important deities, heroic ancestors, or celestial animals. Constellations encoded moral lessons, historical memory, and societal priorities. They were used to explain natural events, justify rituals, and reinforce social cohesion. Observation of the sky became inseparable from cultural meaning. Humans experienced the night not as empty space, but as a structured, meaningful environment where natural phenomena were linked to life on Earth and human society. The cognitive act of connecting stars into patterns reflects an essential human skill. Early humans imposed structure on the apparent randomness of the night sky, creating maps, stories, and practical tools simultaneously. This ability to see order where others might see chaos allowed for navigation, timing of activities, and transmission of knowledge. It also fostered imagination, giving rise to myths, allegories, and spiritual systems. Observation was never purely technical. It was an integrated process linking mind, culture, and environment. Observing constellations required attention to multiple dimensions: brightness, position, motion, and seasonal changes. Tracking the sky over time revealed repeating patterns and cycles. Early humans noticed the gradual shift of stars due to precession, even if they did not understand the mechanics. The passage of years changed the timing of star risings and settings relative to the calendar, requiring adjustments to ritual or practical schedules. This long-term attention demonstrated that early astronomy combined acute perception with temporal awareness, creating knowledge that spanned generations. In Egypt, Mesopotamia, China, and Mesoamerica, constellations were integrated into architecture. Temples, pyramids, and ceremonial sites were often aligned with star risings, solstices, or planetary positions. Observation was formalized into planning and construction. Lines, angles, and positions recorded in stone preserved knowledge for centuries. These alignments illustrate the interplay between empirical observation and cultural priorities, showing that the sky shaped both thought and material practice. Mapping similarities and differences across civilizations reveals universal patterns in human cognition. Bright, regular, or easily recognized stars were prioritized. Clusters became anchors for observation. Mythology, ritual, and society shaped interpretation, but did not alter the underlying observation. Humans everywhere relied on the night sky as a predictable reference frame. Despite geographical distance and cultural diversity, observation followed similar principles. noticing repetition, marking significance, and encoding knowledge for survival and cultural continuity. Cultural exchange and independent discovery both contributed to the development of constellations. Trade routes, migration, and contact between groups allowed some knowledge to spread, while shared human perception ensured that other patterns arose independently. In all cases, observation required patience, memory, and attention to subtle details. The same night sky produced different constellations and stories, yet all were grounded in the same empirical reality. This duality between universal observation and local interpretation defines human engagement with the heavens. Constellations became teaching tools. Oral traditions passed from elders to children included not only stories, but precise instructions on locating stars and understanding their movements. Songs, chants, and gestures reinforced the positions and sequences of star clusters, allowing knowledge to persist without writing. The repetition of observation combined with cultural encoding enabled societies to maintain sophisticated astronomical awareness over generations, ensuring that critical survival information was preserved alongside myth and ritual. Finally, constellations provided a shared framework for interpreting celestial events. They enabled humans to distinguish between ordinary stars, wandering planets, and unusual phenomena like comets or eclipses. By placing these events within the structure of familiar constellations, observers could communicate about them, predict their recurrence, and integrate them into cultural meaning. Across continents, constellations became a bridge between observation, cognition, and society, linking practical knowledge with the stories, beliefs, and priorities of human civilizations. Humans learned early that the sky could be used to measure time. Observing the sun, the moon, and the stars allowed them to organize life in cycles. The solar year, marked by the sun's journey along the horizon, defined the rhythm of seasons. The longest and shortest days were easily noticeable. In summer, daylight stretched far into the evening. In winter, night dominated the sky. Early observers recorded these changes, often using stones, posts, or markings in the landscape to note the sun's rising and setting points. These observations became the foundation of solar calendars, which guided planting, harvesting, and ceremonial activity. Lunar cycles were equally important. The phases of the moon, from new to full and back, occurred in roughly 29-day sequences. Humans used this cycle to structure months, which were easy to count and observe. The combination of solar and lunar cycles created a natural rhythm for organizing time. In some regions, the lunar month was favored, while in others, the solar year took precedence. Over centuries, humans learned to reconcile the differences between the two, noting that 12 lunar months fell slightly short of a solar year. This understanding led to the introduction of intercalary days or months, inserted to keep the calendar aligned with the seasons. Stonehenge, in England, illustrates the sophistication of early solar observation. Its massive stones are positioned to mark sunrise at the summer solstice and sunset at the winter solstice. The precision of alignment suggests careful, repeated observation over many years. Observers would have noted the sun's position each day, recording its movement against fixed stones or distant markers. By watching for the longest and shortest days, humans could predict seasonal changes and plan activities accordingly. Stonehenge was not merely a monument. It functioned as a calendar, a ritual site, and an observatory, combining practical and spiritual purposes. The Goseck Circle in Germany provides another example. Constructed of wooden posts in a circular arrangement, It aligns with the rising and setting of the sun on the solstices. The builders clearly understood the sun's yearly path and used it to determine key points in the agricultural cycle. The structure's placement and design suggest that precise measurement and repeated observation were central to its function. It reflects the human need to connect celestial cycles with daily life, structuring time in a way that guided work, ritual, and social organization. In Egypt, Nabta Playa demonstrates early integration of celestial observation with both practical and ceremonial life. Stone arrangements there align with the summer solstice, indicating a careful understanding of the solar cycle. These observations helped predict the annual flooding of the Nile, which was crucial for agriculture. By knowing when the river would rise, communities could plan planting and harvesting to ensure survival. Celestial events were therefore both a practical guide and a symbolic framework, linking the heavens to the earth in tangible, observable ways. Tracking celestial cycles required careful attention to detail. Observers noted the rising and setting of stars, the phases of the moon, and the apparent movement of the sun across the horizon. Patterns were recorded using physical markers, oral instruction, or simple notations on bone, wood, or stone. Repeated observation over months and years improved accuracy, allowing humans to anticipate events and align their activities with natural rhythms. This cumulative knowledge was a form of applied science, developed long before formal mathematical or astronomical theory. Festivals and rituals were closely tied to these cycles. Communities observed solstices, equinoxes, and key lunar phases as occasions for gathering, feasting, or ceremonial activity. These events marked transitions in the year, reinforcing social cohesion while reflecting the practical importance of celestial timing. In some regions, the appearance of particular stars or constellations indicated the start of the important festivals or planting seasons. Observation of the night sky became intertwined with social and religious life, creating a cultural calendar embedded in celestial phenomena. The precision achieved by early observers is evident in the alignment of ancient structures. Large stones or posts were positioned with remarkable accuracy to mark solar or lunar events. This required careful measurement, repetition, and long-term observation. Observers would note subtle shifts over the year, record changes, and adjust placement or interpretation accordingly. These practices demonstrate a sophisticated understanding of astronomical cycles, showing that humans could achieve highly accurate predictions through patient, repeated observation without modern instruments. Solar and lunar calendars were also used to coordinate activities over larger regions. Agricultural cycles depended on rainfall, temperature, and seasonal growth, which could vary locally. By aligning work with the movement of the sun, moon, and stars, communities could synchronize planting and harvesting. Festivals and social events were also timed with celestial events, ensuring coordination among groups. This integration of astronomical observation with practical and social needs reflects a holistic approach to timekeeping, linking human activity directly to the movements of the heavens. The use of intercalary months or days illustrates the flexibility and refinement of early calendars. Observers realized that 12 lunar months were slightly shorter than a full solar year. To prevent drift, extra days or months were added at intervals. This adjustment required awareness of long-term patterns and careful tracking of the sun and moon. The practice shows that early humans were not only recording what they saw, but also analyzing and correcting for discrepancies, demonstrating an early form of empirical reasoning. Observation of the sky was continuous and cumulative. successive generations added to the knowledge of their predecessors, refining calendars, noting subtle shifts in celestial cycles, and preserving information in both physical and oral form. Stone alignments, wooden posts, and simple markings all contributed to a growing body of knowledge that allowed humans to predict solstices, equinoxes, lunar phases, and eclipses. This cumulative process represents the first sustained scientific endeavor, relying on repetition, careful attention, and verification over time. Astronomical observations supported both survival and planning. In agricultural societies, timing of planting and harvesting determined food supply and community stability. In pastoral communities, the movement of the sun, moon, and stars guided migration and seasonal grazing. Even small errors in timing could have serious consequences. The accuracy of early calendars was therefore essential, and careful observation of celestial events became a practical necessity, not just a curiosity or ritual practice. The integration of astronomy into daily life is also evident in festivals and ceremonial events. Celebrations often coincided with solstices, equinoxes, or particular lunar phases. Rituals were performed at times when the sun, moon, or stars reached specific positions in the sky, connecting human activity with cosmic cycles. This synchronization reinforced both social cohesion and environmental awareness. By observing and responding to celestial patterns, humans linked their lives to the predictable rhythms of the heavens, creating a structured and meaningful experience of time. Long-term observation allowed early humans to detect subtle changes. The sun's path shifted slightly over decades due to axial precession, and lunar and planetary positions varied over longer periods. Observers who kept records could detect these slow changes, adjust calendars, and refine predictions. Such attention to detail illustrates the sophistication of early timekeeping, showing that practical observation was combined with long-term empirical monitoring. The use of stone circles, posts, and other markers reflects a deep understanding of geometry and alignment. Observers had to note angles, rising and setting points, and distances, creating frameworks that could be repeatedly observed and tested. The physical structures acted as extensions of human perception, allowing precise observation and reinforcing memory. They also ensured that knowledge could be transmitted across generations, preserving the accuracy of timekeeping and calendar systems. The combination of solar and lunar observations allowed early humans to anticipate both daily and seasonal changes. Moon phases provided a short-term measure of time, while solar observation marked the year's progression. By observing both, humans could coordinate planting, harvesting, hunting, and ceremonial activities with precision. This integration of multiple celestial cycles demonstrates a sophisticated understanding of natural rhythms, reflecting an empirical approach to time that balanced practicality with observation. Calendrical knowledge was not isolated. Observation of the sky influenced social organization, ritual timing, and even political authority. Leaders often relied on astronomers or priests to determine auspicious times for planting, construction, or ceremony. Accurate timekeeping conferred practical advantages, ensuring survival, resource management, and social cohesion. The night sky became a shared reference frame, connecting human activity with predictable, observable cycles of the cosmos. Finally, repeated observation reinforced accuracy and reliability. Early humans noticed patterns, tested predictions, and recorded outcomes. Over years, this process refined their understanding of solar, lunar, and stellar cycles. Knowledge of solstices, equinoxes, moon phases, and planetary positions became precise enough to support both survival and ritual life. Timekeeping evolved into a structured system, rooted in observation, memory, and physical markers, demonstrating that humans could measure, predict, and respond to celestial cycles without modern technology. Through careful study of the heavens, ancient people transformed the night sky into a living calendar, guiding life on Earth with subtlety, precision, and enduring insight. Early humans noticed that not all points of light in the sky behaved in the same way. Some stars remained fixed relative to others, maintaining consistent patterns across nights and seasons. Others, however, moved in ways that seemed unusual. These were the planets, known as wandering stars, to many ancient cultures. Mercury, Venus, Mars, Jupiter, and Saturn were bright enough to be seen without telescopes, and their movement caught the attention of careful observers. Unlike the fixed stars, which rotated predictably around the North Star or other points of reference, the planets wandered along the paths of the ecliptic, slowly shifting position over weeks and months. This movement was puzzling, yet it was predictable enough to be recorded and interpreted. Venus, the brightest of the planets, was particularly prominent. Its appearance either in the early morning before sunrise or in the evening after sunset made it a constant marker across months. Observers noticed that Venus did not follow the same rhythm as the stars. It appeared, disappeared, and returned according to a cycle. Mercury, closer to the Sun, was more difficult to track, often appearing near sunrise or sunset, while Mars stood out with its reddish hue. Jupiter and Saturn moved more slowly across the sky, but were noticeable due to their brightness and steady motion. By comparing the positions of these wandering lights against the background of fixed stars, humans could differentiate planets from the constellations. Retrograde motion was particularly striking. At times, Mars, Jupiter, or Saturn appeared to move backward relative to the stars before resuming its forward path. This apparent reversal puzzled observers, who relied solely on naked eye observation. They recorded these motions carefully, sometimes over years, creating early logs of celestial behavior. The retrograde phenomenon was not random. It followed a pattern connected to the relative motion of Earth and the planets. While early humans did not understand the mechanics of orbits, they were able to recognize regularity in these apparent anomalies, noting when the wandering stars reversed direction and when they resumed their normal course. The planets were embedded in cultural interpretation. In Mesopotamia, Babylonian astronomers associated Mars with Nergal, the god of war, and Jupiter with Marduk, a deity representing order and kingship. Venus was linked to Inanna, or Ishtar, reflecting themes of love, fertility, and duality. Observers saw patterns in planetary motion and associated them with events on Earth, such as conflicts, prosperity, or seasonal cycles. Similar associations occurred in Egypt, where planets were connected with gods and cosmic order, and in Mesoamerica, where Venus guided ritual and agricultural timing. Observation of planets became both empirical and symbolic, integrating measurement with meaning. The paths of the planets were recorded with increasing precision. Babylonian astronomers used simple grids and tables to log positions against known stars or constellations. They recognized cycles, such as the periodic return of Venus to a similar position in the sky after approximately 8 years. This long-term tracking allowed for predictive observation. Knowing when a planet would appear, disappear, or reverse its path helped anticipate events or plan rituals. Predictive astronomy emerged from this careful observation, linking repeated measurement with expectations about the future behavior of celestial objects. Observation required patience. planets move slowly relative to stars, so nightly monitoring was necessary. Observers compared positions to reference stars, noting changes over weeks. Memory, oral instruction, and physical markers aided this process. In some cultures, temples, pillars, or sighting stones were aligned to help track planetary movement. Careful repetition of observation over months and years allowed early humans to establish reliable patterns, turning wandering stars into predictable guides despite their irregular appearance to casual viewers. The recognition of planetary cycles laid the groundwork for early calendars. Lunar months, solar years, and planetary motion could be integrated to anticipate seasonal and ceremonial events. Venus's cycle, for example, influenced festival timing in Mesoamerica. Jupiter and Saturn, with longer orbital periods, provided markers for multi-year cycles, helping track longer-term events such as political succession or ceremonial cycles. Observation of planets was not merely academic. It provided a temporal framework for societies to coordinate activities, rituals, and agricultural planning. Cultural interpretation extended to astrology in many regions. While the predictive power of planets was empirical in terms of visibility, humans also associated their positions with human or natural events. Mesopotamian records show detailed correlations between planetary positions and omens, documenting when certain configurations coincided with wars, floods, or prosperity. These interpretations were structured, reflecting the observation of real motion, while embedding it in social meaning. This combination of careful observation and symbolic association exemplifies how humans integrated empirical data with cultural context. Tracking retrograde motion required an understanding of sequences and recurrence. Observers noticed that planets followed a repeating cycle: forward movement, retrograde reversal, stationary points, and return to normal motion. By mapping these intervals, astronomers could anticipate future behavior, allowing them to predict when a planet would appear in a particular constellation. This predictive power was a significant achievement, demonstrating that human observation could extract order from apparent complexity. Even without instruments or theoretical models, the planet's brightness and color helped differentiate them from stars. Mars's red hue, Venus's brilliance, Jupiter's steady light, and Saturn's subtle tint allowed observers to identify them consistently. Brightness reinforced recognition and memory, assisting in tracking over long periods. By combining color, motion, and position relative to the fixed stars, humans could create a mental map of planetary paths that was both practical for timekeeping and meaningful within cultural narratives. Observation of the planets was also connected to the sky as a whole. Their paths lay along the ecliptic, the apparent path of the sun. Observers noted that the moon and planets followed roughly the same path, while stars moved in parallel patterns around the poles. This understanding allowed humans to contextualize the wandering stars within a larger celestial framework, linking multiple cycles together. Knowledge of the ecliptic and planetary paths helped anticipate conjunctions, alignments, and other notable events in the sky. Temples and observatories were often constructed to facilitate planetary observation. Elevated platforms, sightlines through pillars, and open spaces allowed precise tracking. In Babylon, scribes recorded positions over decades, producing tables of planetary motion. In Mesoamerica, observations of Venus guided ceremonial and agricultural timing, demonstrating practical application. Observers learned to correlate positions with intervals and cycles, creating a foundation for predictive astronomy that was remarkably effective despite limited technology. The observation of planets contributed to numerical and mathematical development. Recording positions required counting, measuring intervals, and noting differences in motion. Repeated observation led to an understanding of periods, cycles, and proportional relationships. Even without formal equations, humans developed methods to calculate when a planet would reappear or return to a given location, linking empirical observation to quantitative reasoning. Planetary motion also provided a context for recognizing anomalies. Eclipses, comets, and unusual planetary alignments stood out against expected patterns. Observers could distinguish between regular, predictable motion and rare events. This awareness of order and deviation laid the groundwork for later systematic astronomy, teaching humans to rely on careful measurement, record keeping, and pattern recognition. The wandering stars influenced cultural storytelling as well. Mars could be a warrior god, Venus a guide for planting or fertility, Jupiter a ruler of order, Saturn a marker of cycles. These associations reinforced observation, making patterns easier to remember and communicate. Stories encoded empirical information, ensuring that knowledge of planetary motion persisted across generations. Cultural meaning and practical observation were inseparable, each reinforcing the other. Cumulative observation over years and decades produced remarkably accurate cycles. Babylonian astronomers could predict Venus's appearance and disappearance, retrograde motion, and conjunctions. They noted Jupiter and Saturn's slow progression across constellations and recorded these movements systematically. This long-term commitment to watching the sky allowed early humans to anticipate events with surprising accuracy, laying the foundation for more advanced astronomy. Observation of the planets required synthesis. Humans compared positions across nights, correlated movements with stars, and recorded patterns. This synthesis of spatial and temporal information formed the basis of early predictive astronomy. Even without understanding orbits or gravity, observers recognized cycles, measured intervals, and learned to forecast future positions of the wandering stars. This ability to extract regularity from apparent complexity demonstrates the ingenuity and persistence of early astronomers. Planetary motion was central to timekeeping. While stars and the sun marked seasons, the planets' unique paths provided additional markers for long-term cycles. These markers guided festivals, agricultural planning, and ceremonial events. By understanding both the regular and irregular motions of celestial objects, humans built a practical framework for coordinating life with cosmic rhythms, integrating observation with daily activity. Overall, the careful study of wandering stars fostered a methodical approach to the night sky. Observers learned patience, attention to detail, and long-term record keeping. They recognized patterns, predicted future events, and connected celestial phenomena to cultural, agricultural, and ritual life. Observation of Mercury, Venus, Mars, Jupiter, and Saturn transformed the night sky from a fixed backdrop into a dynamic system of markers, cycles, and guides. This was early astronomy at its most practical and sophisticated, forming the foundation for systematic understanding of the heavens and human engagement with cosmic time. Ancient humans observed that some events in the sky did not follow regular patterns. Unlike the sun, moon, stars, and planets, these phenomena appeared unpredictably, sometimes suddenly. Eclipses, comets, meteors, and bright novae stood out sharply against the familiar rhythms of the night. Their rare appearance drew attention and sometimes fear. People watched carefully when such events occurred, noting the time, position, and appearance. Because they were unusual and dramatic, these phenomena were often linked to events on Earth, from seasonal changes to the fortunes of rulers or the outcome of battles. observation combined with interpretation, blending empirical attention with cultural meaning. Solar and lunar eclipses were among the most striking events. During a solar eclipse, the sun would disappear temporarily, leaving a dark circle in the sky, sometimes accompanied by a halo or faint light at the edges. A lunar eclipse caused the moon to darken and often take on a reddish tint, a phenomenon now understood as sunlight filtered through Earth's atmosphere. Ancient observers recorded these events carefully, noting the time, location, and appearance. In Mesopotamia, clay tablets showed detailed records of eclipses, including predictions once patterns were recognized. Observers realized that eclipses were tied to cycles of the sun and moon, and they gradually developed methods to anticipate them, reducing uncertainty and linking observation to social or political decision-making. Eclipses carried symbolic weight in many societies. They were often interpreted as omens or messages from the heavens. Kings and rulers sometimes consulted astronomers or priests before responding to eclipses, because such events could be taken as signs of divine favor or warning. In China, meticulous records of eclipses allowed the court to prepare rituals intended to protect the emperor, reflecting the belief that celestial phenomena influenced governance. In Mesopotamia, predictions of eclipses became a tool of authority, reinforcing the importance of careful observation and knowledge of celestial cycles. Here, practical astronomy was inseparable from social and political life. Comets were another source of fascination and concern. A comet's sudden appearance, often with a bright head and trailing tail, was difficult to predict. Ancient observers recorded their arrival, duration, and appearance, noting size, brightness, and direction. Comets were sometimes associated with war, famine, or other disruptions. In Babylonian, Chinese, and Roman records, comets were interpreted as warnings or signs, yet observation was empirical. Repeated appearances over decades allowed humans to recognize patterns, even if precise prediction remained elusive. Observing comets required attention, memory, and careful record-keeping, demonstrating the same disciplined approach applied to stars and planets, but applied to rarer and more unpredictable events. Meteors and meteor showers were also noticed. Bright flashes across the sky drew immediate attention, and clusters of meteors at predictable times became associated with recurring events. Observers tracked the appearance of meteor showers relative to the constellations, linking them to annual patterns. Even when meteors were isolated, observers recorded direction and color, creating a mental map of unusual celestial phenomena. The fleeting nature of meteors required attentiveness, and the human ability to notice, memorize, and interpret such brief events demonstrates remarkable observational skill. Their unpredictability enhanced their symbolic significance, often woven into cultural stories or omens. Supernovae, although rarer, were recorded when they appeared. A star suddenly brighter than usual, sometimes visible even during the day, could be noticed and remembered. Ancient Chinese astronomers, among others, documented guest stars, noting their location relative to familiar constellations and their duration of visibility. These observations provided both empirical evidence of change in the heavens and the basis for cultural interpretation. The sudden brightness and disappearance of a supernova reinforced the impression that the heavens were active, dynamic, and capable of influencing life on Earth. Empirical observation and myth often existed side by side. While eclipses, comets, and meteors were recorded with care, they were also interpreted through cultural lenses. Stories attributed them to gods, spirits, or cosmic forces. Observers could predict the timing of some phenomena, like lunar eclipses, yet the dramatic effect reinforced the need for narrative explanation. This dual approach allowed societies to integrate rare events into practical planning, ceremonial life, and social understanding. Observation provided reliability, while myth and prophecy provided meaning. Recording of unusual events required structured methods. In Mesopotamia, scribes noted comets, eclipses, and meteors in cuneiform on clay tablets, linking their appearance to seasons, festivals, or political events. In China, meticulous chronicles were maintained for centuries, logging eclipses, guest stars, and meteor appearances in relation to emperors and states. These records show that even unpredictable phenomena could be studied systematically, allowing humans to anticipate future occurrences, recognize patterns over long periods, and incorporate these into social and political practice. Cultural interpretation shaped the perception of significance. A solar eclipse might be seen as a threat to a king or as a cosmic reset. Comets could symbolize disaster, while meteors might signal the arrival of ancestors or gods. Supernovae were often described as heavenly messengers. Observation was empirical, yet meaning was layered onto it. Humans learned to respond practically, preparing rituals, adjusting ceremonies, or recording events, while maintaining a narrative framework that integrated unusual occurrences into cultural understanding. Despite the unpredictable nature, repeated observation revealed patterns over time. Lunar eclipses occur in cycles, comets return along known paths, and meteor showers repeat annually. Over generations, careful tracking allowed humans to recognize these cycles. Ancient observers could then predict the timing of future events, sometimes years in advance. The ability to distinguish predictable phenomena from truly exceptional events reflects an advanced awareness of regularity and variation in the sky, providing both practical knowledge and cultural authority. Integration of unusual phenomena into mythology reinforced learning and observation. Stories preserve positions, appearances, and timing, encoding empirical knowledge in memory and tradition. Oral and later written records acted as repositories for observation, allowing societies to pass information without formal scientific instruments. Memory and narrative became tools for empirical verification, ensuring that rare events were not forgotten and that knowledge accumulated over generations. Observation of eclipses and comets also required understanding context. Seasonal position, time of night, and surrounding constellations were noted to determine significance. Accuracy depended on reference to the familiar patterns of stars and planets. By situating unusual events against the regular framework of the sky, humans could record both their rarity and their place in the larger celestial order. This method allowed for both prediction and interpretation, linking observation, memory, and culture. The societal impact of these phenomena was profound. Kings, priests, and leaders often relied on astronomers to interpret signs. Rituals, political decisions, and ceremonial planning were influenced by predicted or observed events. Control of astronomical knowledge reinforced authority, while accurate observation maintained stability. Knowledge of eclipses, comets, and meteors became both a practical tool and a source of social power, intertwining science, culture, and governance. Observations also fostered mathematical and chronological reasoning. The timing of eclipses, for instance, revealed intervals and cycles. Patterns in comet appearances encouraged tracking over decades. Recording these events required counting, measuring, and correlating with regular celestial markers. This careful documentation was an early form of scientific methodology, combining systematic observation with analysis, even without formal equations or models. Humans were building predictive frameworks based on repeated experience and recorded evidence. Interpretation of celestial omens was guided by prior knowledge. By knowing the normal cycles of the sun, moon, planets, and stars, observers could recognize anomalies. These deviations were significant, capturing attention and prompting action. The ability to distinguish routine motion from rare events reflects both careful empirical observation and cognitive skill. Observers developed a layered understanding of the sky, where the ordinary and extraordinary were recognized, documented, and understood within a practical and symbolic framework. In addition to written records, some societies used monuments and alignments to mark unusual events. Solar and lunar eclipses could be anticipated using horizon markers, while other structures might be aligned with predicted celestial positions. This combination of observation, construction, and record-keeping enhanced the precision of early astronomy, enabling humans to integrate unpredictable phenomena into predictable frameworks, bridging empirical observation with cultural interpretation. The integration of empirical observation and myth provided resilience. Knowledge of eclipses, comets, and meteors could be applied in practical planning, while narrative provided social cohesion and meaning. Over time, repeated observation allowed humans to recognize cycles and patterns even in rare phenomena, gradually transforming uncertainty into understanding. The heavens were no longer entirely unpredictable. Through careful attention, record-keeping, and interpretation, early humans were able to anticipate events, contextualize them, and link them to the rhythms of earthly life, combining science and culture in a way that sustained knowledge across generations. Ancient humans found ways to preserve what they observed in the sky. The night sky, full of stars, planets, and the wandering lights of the sun and moon, was complex. To keep track of patterns, people developed visual star charts and diagrams. In Mesopotamia, clay tablets were inscribed with constellations, planetary positions, and records of eclipses. These tablets were small enough to handle but detailed enough to record repeated observation. By drawing stars in relative positions or marking the rising and setting of planets, early astronomers created a visual framework that could be studied, taught, and referenced over time. Knowledge of the night sky was therefore not fleeting. It could survive beyond a single observer's lifetime. In Egypt, diagrams showed the movement of the sun, moon, and planets along the ecliptic. These illustrations were often simplified, emphasizing the brightest stars and most significant celestial events. Lines connected stars, representing constellations or movement across the sky. Diagrams were not decorative alone. They encoded information about time, direction, and ritual cycles. By comparing diagrams from one season or year to another, observers could identify patterns, track anomalies, and predict future events. Maps served as both educational tools and references for ongoing observation. The development of tools enhanced the accuracy of observation. Gnomons, simple vertical posts casting shadows, allowed observers to track the sun's path and measure solstices and equinoxes. By noting the length and direction of shadows, early humans could mark the passage of the year and determine the timing of agricultural or ceremonial activities. The simplicity of the tool did not limit its effectiveness. Careful, repeated observation allowed precise tracking of solar motion without instruments beyond the gnomon itself. Merkets, used in ancient Egypt, were another practical device. A merket consisted of a sighting instrument aligned with a star or a star's rising point on the horizon. Observers used these to determine true north or to monitor the movement of specific stars over time. Precision was achieved through repeated alignment, attention to detail, and consistent observation, demonstrating that even basic tools could produce reliable astronomical knowledge. Observers could measure angles, track positions, and anticipate celestial events with impressive accuracy. In Mesopotamia, simple sighting sticks and horizon markers performed a similar function. By aligning the stick with a rising or setting star, observers recorded the position against landmarks. Over days, months, and years, this method provided data on seasonal changes, planetary movement, and important festival timing. Such tools allowed humans to transfer knowledge orally and practically, reinforcing memory while creating a physical connection to the observed sky. Observation became an active process, involving both the mind and the body in recording and interpreting celestial phenomena. Early astrolabes, though more advanced, emerged as extensions of these methods. Portable and geometric, they allowed users to model the positions of stars and planets at given times. Even in simple forms, the astrolabe provided a visual and manipulable representation of the sky. By rotating parts or aligning sites, observers could predict the movement of celestial bodies, check rising and setting times, and plan ceremonies or agricultural tasks. The astrolabe shows how observation, measurement, and abstraction were combined into tools that expanded the human capacity to understand and use the sky. Maps and charts helped preserve knowledge across generations. Written records, diagrams, and simple instruments ensured that information did not rely solely on memory. Teachers could show students the relative positions of stars, the movement of planets, and the timing of eclipses. Repetition and demonstration reinforced empirical knowledge while maintaining continuity. Across regions, similar methods allowed societies to maintain sophisticated awareness of the sky, even without direct contact, showing that cumulative observation could produce long-lasting understanding. The creation of star maps required attention to detail. Observers noted brightness, relative positions, motion, and seasonal changes. Constellations, planetary paths, and lunar phases were plotted in relation to each other. Errors could be corrected over time through repeated observation and comparison with previous records. Maps were therefore dynamic tools, refined over years to achieve practical accuracy. By translating the sky into visual diagrams, humans could study the heavens systematically, preserving both practical and cultural knowledge. Tools reinforced observation and learning. Using gnomons, merkets, sighting sticks, or astrolabes, observers could link measurement to memory. Marks on the ground or diagrams on clay tablets allowed spatial understanding of celestial motion. Students learned to recognize rising and setting points, track planetary paths, and record eclipses. Observation was methodical, systematic, and cumulative. Knowledge gained through tools and maps could be transmitted across generations, ensuring continuity of understanding and precision over time. Star maps and diagrams also connected human activity to the night sky. Agricultural calendars were derived from the rising and setting of stars recorded in maps. Rituals were timed to celestial events noted on charts. Observation, measurement, and representation created a cycle of knowledge in which the sky informed life on Earth. Through maps, tools, and diagrams, humans could interact with the heavens in a practical, repeatable way, integrating observation into survival, culture, and ritual. Accuracy without telescopes was remarkable. Repeated observation, careful notation, and consistent use of tools allowed early humans to predict solstices, eclipses, planetary motion, and seasonal changes. The precision achieved relied on attention, patience, and methodical practice. Even in simple societies, naked-eye astronomy combined with diagrams and instruments produced reliable, long-term knowledge of celestial cycles. Maps preserved not just empirical observation, but also cultural meaning. Constellations, planetary associations, and significant events were encoded in diagrams, ensuring that the practical and symbolic dimensions of astronomy were maintained. A single chart could convey direction, timing, prediction, and myth simultaneously. Knowledge was therefore both scientific and cultural, a multi-dimensional record of human engagement with the night sky. The cumulative effect of tools and maps was profound. Observation became repeatable, teaching could occur systematically, and knowledge could be checked and refined over time. Civilizations could maintain continuous records of solar, lunar, and planetary motion, linking generations of observers. By standardizing methods of measurement and representation, societies ensured that knowledge of the night sky would survive beyond immediate experience, forming the foundation for advanced astronomy in later periods. Finally, the integration of star maps, diagrams, and tools allowed humans to conceptualize the sky as a structured system. Observation was no longer fleeting or personal. It could be shared, taught, and verified. Celestial patterns were mapped, movement was recorded, and predictions could be made. By preserving knowledge across generations, humans created continuity, enabling the night sky to serve not only as a guide for survival, but as a lasting framework for cultural, practical, and scientific understanding. The night sky inspired more than practical knowledge. It influenced culture, art, and the way societies understood themselves. People saw the stars not only as guides for planting or navigation, but also as symbols that connected daily life to the cosmos. Temples and pyramids were constructed with careful attention to celestial alignment. In Egypt, the Great Pyramids of Giza are oriented toward the cardinal points, and certain passageways align with stars that marked significant moments in the year. This alignment was not accidental. It reflected both a desire to connect the earthly with the divine and a deep understanding of the movement of stars and the sun. Monuments across the world display similar attention to the heavens. In Mesoamerica, structures such as the pyramids at Chichen Itza align with equinox sunlight, creating striking visual effects that mark seasonal change. The placement of buildings and plazas often corresponded with solstices, lunar cycles, and planetary positions, linking architecture to observable patterns in the sky. Observation of the heavens became a tool to shape physical space, embedding celestial knowledge into public and sacred environments. In this way, architecture served as both practical calendar and spiritual expression. Art reflected the sky in both abstract and figurative forms. Star patterns, planetary symbols, and depictions of the sun and moon appear in pottery, murals, and carvings across ancient cultures. Bright stars and comets inspired symbolic motifs that conveyed meaning to communities and reinforced cultural memory. In Mesopotamia, cylinder seals depict celestial symbols alongside gods and mythological scenes, showing that astronomical awareness was inseparable from religious and social identity. Art preserved observation visually, ensuring that knowledge of the sky could be shared and remembered. Music and poetry were also influenced by celestial observation. Songs and chants marked the passage of time, the rising and setting of stars, or the phases of the moon. Poetry often included imagery of the sun, moon, and stars, reflecting cycles of life and cosmic order. Rhythms of ritual music were timed to align with celestial events, linking auditory experience with observable changes in the sky. These cultural practices reinforced awareness of patterns, creating shared understanding and participation in the rhythms of the cosmos. Storytelling connected observation to meaning. Myths described the origins of the sun, moon, stars, and planets, often encoding empirical observation within narrative frameworks. Characters, deities, or heroes were placed among constellations, creating memorable associations between celestial positions and cultural memory. These stories help transmit knowledge across generations, preserving both practical and symbolic information. By embedding patterns of movement, cycles, and events in narrative, humans ensured that even complex astronomical knowledge could be retained without written records. The role of astronomy in shaping social hierarchy was significant. Observers of the sky, priests, astronomers, or learned elders, held specialized knowledge that conferred authority. Predicting eclipses, tracking planetary motion, or determining the timing of festivals gave these individuals influence over ritual, agriculture, and political life. The ability to understand the heavens separated roles within society, creating expertise that was both practical and symbolic. Celestial knowledge thus became a foundation for social structure and governance, reinforcing the connection between observation and leadership. Ritual practice often mirrored celestial cycles. Festivals, ceremonies, and processions were timed to solstices, equinoxes, lunar phases, or planetary events. Participants experienced the rhythms of the sky physically and emotionally, linking human activity to cosmic patterns. Through coordinated observation, ritual, and public expression, communities internalized the structure of time and space as reflected in the heavens. Astronomy, therefore, was not abstract. It was enacted, lived, and celebrated in ways that shaped collective experience. The integration of astronomy into architecture, art, and ritual also served educational purposes. Observation, alignment, and representation taught successive generations to recognize patterns, anticipate events, and appreciate the order of the cosmos. Students learned by seeing monuments aligned with stars, hearing songs timed to celestial rhythms, or listening to stories encoded with astronomical information. Knowledge of the sky became experiential, combining sensory, intellectual, and cultural learning into a cohesive framework that guided thought and behavior. Cultural expression through the sky created continuity across generations. Artworks, monuments, music, and stories preserved empirical observation and symbolic meaning. The patterns of the night sky were not fleeting. They were embedded in society's memory and material culture. By linking practical observation with creative expression, societies maintained both knowledge and identity, ensuring that the night sky remained a central reference point in understanding the world. Finally, the integration of astronomy into cultural expression highlights the deep connection humans maintained with the heavens. Observation informed architecture, ritual, music, storytelling, and social organization, while culture reinforced the significance of the sky. The night sky was thus a canvas, a clock, a guide, and a source of inspiration, shaping human perception, action, and belief in ways that endured for centuries and left a lasting imprint on both material and intangible heritage. The observations of ancient peoples did not vanish with time. They formed a foundation for later scientific thought. Naked eye astronomy, practiced across civilizations, eventually gave way to written records and systematic study. The careful tracking of stars, planets, eclipses, and comets provided data that could be examined, compared, and preserved. Clay tablets, stone inscriptions, diagrams, and oral traditions became tools for continuity, allowing knowledge to transcend generations and geographical boundaries. By transforming observation into recorded evidence, ancient societies created a bridge between experience and analysis, laying the groundwork for more formalized science. Greek astronomers built on this inherited knowledge, combining empirical observation with geometry and reasoning. They incorporated the catalogues of Babylonian scholars, noting planetary motion, lunar phases, and eclipses. Greek thinkers developed models to explain the apparent movement of the heavens, while retaining a reliance on careful, repeated observation. Tools such as the astrolabe and armillary sphere allowed precise measurement, and philosophical inquiry complemented empirical methods. By connecting inherited observations with abstract reasoning, Greek astronomy elevated the study of the sky from a practical and ritual activity to a theoretical science, while still rooted in careful observation. In India, early astronomers also preserved and refined celestial knowledge. Texts such as the Vedanga Jyotisha describe methods for tracking the sun, moon, and planets, calculating calendars, and predicting eclipses. Observational methods emphasize cycles and repetition, reflecting the legacy of earlier civilizations. Planetary motion, solstices, equinoxes, and lunar phases were incorporated into both practical calendars and ritual timing. The combination of observation, mathematics, and cultural significance demonstrates continuity. Humans across regions maintained systematic attention to the night sky, adapting inherited methods to local practice and expanding their predictive capacity. Islamic astronomy absorbed knowledge from Greek, Indian, and earlier Middle Eastern sources. Observatories were established, astronomical tables created, and instruments refined. Scholars translated texts, preserved empirical records, and developed new methods for predicting planetary motion and eclipses. Instruments such as astrolabes and sextants allowed precise tracking, yet the foundational methods, careful naked-eye observation, cyclical recording, and alignment with landmarks, remained central. Through these contributions, ancient methods endured, influencing navigation, timekeeping, and scientific thought for centuries, linking the practices of distant observers in a continuous chain of knowledge. Constellations and myths persisted across time and culture. The patterns recognized by Mesopotamians, Egyptians, Chinese, and Mesoamericans became standardized in later traditions. Greek mythology codified constellations, naming stars and recording their positions. The stories associated with celestial patterns survived orally and in writing, preserving both cultural identity and empirical knowledge. Even today, modern astronomy retains these names and patterns, demonstrating that observation and interpretation created a legacy that bridges ancient and contemporary perspectives. The methods developed by early observers also continue to influence modern science. Recognizing periodicity, recording positions, and predicting events are core practices in astronomy. Simple tools, careful observation, and repeated measurement laid the foundations for more sophisticated instruments. Yet the principles remain consistent. Observers of the past demonstrated that accuracy does not require technology alone. Attention, patience, and systematic study are as essential today as they were millennia ago. Modern viewers can reconnect with the ancient sky by returning to naked-eye observation. Away from city lights, the Milky Way stretches across the heavens as it did for early humans. Bright planets, comets, and meteor showers appear according to predictable cycles. just as they did thousands of years ago. Observing the moon's phases, noting the rising and setting of stars, and recognizing the patterns of constellations allow a direct experience of the same sky that guided, inspired, and structured ancient societies. This connection fosters both appreciation of human ingenuity and a sense of continuity with those who first looked upward. Understanding the ancient sky also deepens perspective on culture and science. Observation shaped calendars, rituals, architecture, and mythology. Knowledge of cycles informed agriculture, governance, and social organization. Myths and art encoded empirical observation, ensuring that practical knowledge was preserved alongside cultural expression. Modern astronomy, though far more detailed and instrument-driven, rests on these foundations, recognizing patterns, tracking motion, and seeking understanding of cosmic order. The night sky continues to inspire, just as it did for ancient observers. Celestial phenomena, planets, stars, eclipses, comets, remind us of cycles that surpass a single human lifetime. By observing, recording, and interpreting the sky, early humans created systems of knowledge that were both practical and symbolic. These practices endured, evolving into written science and advanced astronomical methods. Yet the core remains: careful observation, attention to pattern, and engagement with the cosmos. Ancient skywatchers looked up with wonder, curiosity, and discipline. Modern viewers can experience the same mix of awe and understanding. Even small acts, like tracing constellations with the hand or noting the phases of the moon, recreate the observational practices of the past. Aligning structures, timing activities with celestial events, and recording occurrences reflect continuity in human experience. Knowledge of cycles allows anticipation of natural phenomena, connects society to seasonal rhythms, and provides a sense of order in the vast sky. By recognizing the persistence of patterns, humans today share the cognitive framework that ancient observers developed. Ultimately, the legacy of the ancient sky is both intellectual and emotional. It is intellectual in the sense that methods, observations, and predictive techniques were preserved and refined across civilizations. It is emotional because the same stars, planets, and patterns that inspired awe, guided ritual, and structured life for ancient peoples continue to evoke wonder today. The night sky serves as a bridge, linking the practical, cultural, and spiritual dimensions of human experience across time. Through observation, recording, and interpretation, early humans created a legacy that continues to inform and inspire, connecting modern observers with the rich heritage of the cosmos. The night sky, when viewed without artificial light, remains a canvas of constellations and planets, a reminder of continuity. Each rising and setting of stars, each cycle of the moon, and each predictable movement of planets carries echoes of the meticulous attention of early observers. Ancient myths, monuments, and diagrams reflect not only belief, but also methodical understanding. Modern astronomy, while more sophisticated, honors these beginnings, demonstrating that humanity's engagement with the sky is both enduring and cumulative. In reconnecting with the stars, we participate in a tradition that spans millennia. Observers long ago used patience, memory, and careful notation to understand patterns that structured their world. By looking upward today, noting familiar stars, and recognizing the cycles they follow, we engage in the same practice, watching, understanding, and reflecting on the order of the cosmos. The legacy of the ancient sky is a reminder that observation, curiosity, and careful recording are timeless tools for human understanding. Through these connections, the ancient sky remains alive, Constellations continue to guide. Planets mark cycles, eclipses and comets remind us of rare events, and myths preserve cultural memory. The practice of observation bridges generations, showing that human engagement with the cosmos is persistent, practical, and inspiring. By following the methods and appreciating the patterns identified by ancient observers, modern viewers can experience the sky as both a scientific and cultural landscape, reconnecting with knowledge that has endured across thousands of years.